Welcome back to the deep learning video lecture series. In the previous class, we had very quick overview of different gradient descent algorithms, and today I would like to give a overview of gradient descent optimization algorithms. So here I am going to mainly emphasize on this update rule, because that is only the thing we need to concentrate here, how the gradient been updated. So then next one is what are the advantages and disadvantages of each gradient descent algorithm. So first let us see the batch gradient descent, because as I said, the gradient descent algorithms are mainly classified into the three categories based on the number of samples are used to train the model or number of samples are used to update the gradient descent. So if you look at the batch gradient descent updates after evaluating all the samples in the data set. So like suppose the theta is a parameter that is need to be updated. So then we have to reduce this, that is by with the learning rate theta, and then the gradient and this is y. The y is output and x is the input. So the cost function, gradient of a cost function. So this is learning rate. We have already discussed what is the impact of a learning rate, and now in this lecture also we will discuss a little about that. And this is a cost gradient function, that is a loss function. The gradient need to be calculated with respect to the, that is a loss would be calculated based on the expected output and the actual output, and then this is the gradient and the learning rate, and this is the, like suppose the parameter that is need to be updated. So that means after evaluating all the samples, it update the weight or the respective parameters. So that is the model will be updated after evaluating all the samples. So let us see what are the pros. And the stable convergence. Convergence means like, so when it reaches the optimal solution. So that is the thing. So the convergence, the stable convergence means the smooth and consistent decrease in the cost function. Like suppose if you take this curve, the function here, like suppose this is the starting point and then the learning starts, that is each step that is depends on the learning rate, and it will come to the optimal solution. Okay, so how this convergence happened, whether it is a smooth convergence or that is means consistent and decrease in the cost function or not. Next one is a global minimum. So global minima, that is when a non-convex, like suppose if you take this curve like this, so in this case this would be considered as a local minima, and this is the lowest point, that is a global minimum. Okay, so our objective function, that is the gradient descent optimization algorithm, that is should update the gradient, that is to reach this global minimum. So a few optimization algorithms like so that will be trapped by this local minima. Okay, so that we will discuss why it will happens. That will be discussed in a couple of minutes. So the global minima more likely to converge to the global minima for convex functions, and the slow for the large data sets, because we need to store the entire data set in the memory, because the parameter will be updated after evaluating all the samples in the data set. So in the real world, there will be millions of the samples also there will be there. So to store all the samples in a data set in a memory, so then the computation will slow down, and the computational cost per the iteration is a high because of this. Next, memory intensive. That means it requires loading the entire data into the memory. So these are the pros and cons of this batch gradient descent. And if you check the use case, like mainly it is used to small to medium sized data sets because of the constraint that we discussed, and the convex optimization problems. Next one is the stochastic gradient descent. So stochastic gradient descent updates, like if you look at the update rule, so theta, that is the parameter, so minus learning rate, and this is going to update. So it is going to calculate the average of all the errors, the cost function, based on the cost function. Like suppose sigma I is equal to 1 to m del f of theta and input, and okay, so it finds like all the gradients, and it takes the average of that, and then it updates. That means for each sample it evaluates and then updates. And if you look at the pros and cons of this stochastic gradient descent, the fast computation, because the quick updates are suitable for the large data sets, because only the one sample will always be stored in the memory, and escape the local minima, because of noisy updates helps to escape the local minima. And noisy convergences means high variance in updates causes the more fluctuations, and it requires more iterations because slower convergence to the optimum. And if you look at the use cases, like online learning, example real-time recommendations, and the large scale data sets. Next, mini batch gradient, that is a set of samples would be selected, a random set of samples would be selected, and then model evaluated and updated. So that is like, suppose if you take the parameter that is to be updated, that is theta, and one, here let us take b sigma equal to I is equal to 1 to b. So delta f, this is the cost function. Okay, so for every batch the gradient would be updated, that is model is updated for every batch. Like suppose we could divide the batch of size 1000 samples, then this would be evaluated and then the parameters would be updated. So if you look at the pros and cons of this mini batch gradient descent, it's a balanced convergence, means combines the speed of a stochastic gradient descent and stability of a batch gradient descent. And efficient computation, that means leverages the vectorization for the fast updates. Next, generalization adds noise to escape the local minima, improve generalization. And the disadvantage is the batch size sensitivity. That means we have to carefully select the batch size, and still noisy, that means more stable than the stochastic gradient descent but less smoother than the batch gradient descent. And if you look at the use cases, the deep learning models like CNN, convolutional neural networks, recurrent neural networks, we use this mini batch gradient descent. and scalable learning with the GPUs and the TPUs. How do we choose the right gradient descent optimization algorithm? And if you look at these three main categories like a batch gradient descent, stochastic gradient descent, and a mini batch. The batch gradient descent use the data set that is a small and fits into the memory when you want the stable and the smooth convergence. Whereas the stochastic gradient is mainly suitable for online learning and the streaming data. So that means a batch of samples would be collected and analyzed, because we will not store this the data which is coming like a stream. And when the fast and frequent updates are required, and then it is better to go for this stochastic gradient descent. Next, mini batch gradient descent. It is mainly recommended for the deep learning models, because of all the deep learning models mainly. Ideal for leveraging the GPUs and TPUs for parallel computation. So it provides a good trade-off between a convergence, speed, and stability. Now you can see just the contour, like how the gradient movement in these three categories of gradient descent optimizations. Like the first figure depicts how the batch gradient descent, how the gradient is moving from the starting point. Let us say this is the starting point and this is the way, and each step is moving, the gradient is moving like this until it reaches the optimal. And if you look at the stochastic gradient descent, because the stochastic gradient descent, it is going to update the model for every sample. So you can see the fluctuation of the gradient like this, in this, like here. And similarly, the mini batch gradient descent, where we select the set of samples, like it's a batch wise update would be done. So the little bit smoother. That means you can find that is it is in between the batch gradient descent and the stochastic gradient descent. So advanced variants and optimizers we have to understand, like momentum, Nesterov accelerated gradient, AdaGrad, and etc. So if you look at the momentum, which accelerate the convergence by considering the past gradients based on the previous gradients, it takes every next step would be evaluated. So that's why it accelerates its convergence by considering the past gradients. So Nesterov accelerated gradient is another very important, which improves the momentum by looking ahead. So not just like, whereas a momentum which accelerates the convergence by considering the past gradients, but whereas the Nesterov accelerated gradient NAG improves the momentum by looking ahead. Next, AdaGrad, because when the gradient is moving towards this the optimal solution, so the velocity not only, okay, so we have to consider the velocity. And like suppose, because if we are not able to control this velocity, like because when we are approaching this optimal solution, we have to control the velocity, otherwise we skip this optimal solutions, and that means we'll jump this optimal solutions. So AdaGrad, that is, adapts the learning rates for each parameter. That means the constant learning rate would not be the best option always. So this model, like this gradient descent optimization algorithms, adopts the different learning rates for each parameters. Next, advanced variants and optimizers are RMS and ADAM. And this RMS probe uses a moving average of a squared gradients for better convergence. This mainly we use in a stock price prediction indicators like moving averages. Next, ADAM, which combines the momentum and the RMS probe, that is popular for the deep learning. So I think we have to discuss mainly how this model, when this model converts to the local minima in gradient descent, what are the possibilities? So that also need to be understood. So because of mainly the many factors which influence this, right? The model would converge to the local minima. The first one is the multiple initializations, that is starting from the different points and select the best results. I think it's yeah. So start from the different points and select the best result. That is the best way. Then the momentum, which helps in escaping the shallow local minimas, and adaptive learning rates. That means different optimizers like Adam and RMS prop adjust the learning rates dynamically. And what are the strategies we need to follow to avoid the local minima? Like non-convex cost function, that is, if the cost function has multiple values, if the cost function has multiple values, the cost function has multiple values, the gradient descent can get trapped in any one of these are all the local minimas. So the cost function would get trapped in any one of them. So initialization, that is a starting point, heavily influences the path of convergence. So that's why we have to take the multiple initializations, that is starting from the different point and selecting the best results. So that is initialization is heavily influences the path of the convergence. Next, poor initialization might lead to the local minima also. Next, another important factor which influences the that is local minima, like a learning rate. So learning rate means we already discussed about this learning rate many times. So the learning rate would be given like in between the 0 to 1. If suppose 0.9, that means the high learning rate. So that means the steps we need to take to move to the optimal solution from the starting point. So suppose if you take big steps, so like suppose this and this is and this and like this. So here we'll jump over the optimal solution. And if you take a very like a small learning rate, then what will happen? If you take the small learning rate, so it may, like suppose, and this is a R, if you take the convex function like this is the function here we have. So it may get trapped in this local minima if the learning rate is very small. Learning rate is what are the steps. So it may get trapped into this local minima. So that is a small learning rate leads to the slow convergence and increase the chances of being stuck, while a learning rate may overshoot the minimum, that is high learning rate. So stochasticity, that is to avoid the local minima, using the stochastic gradient descent introduces the noise, helping to jump out of the local minima. Advanced techniques like methods like a simulated annealing or genetic algorithms are more robust to the local minima. So let us quickly summarize what we discussed in this and what are the key takeaways from this video lecture. In the previous lecture and in this lecture, I mainly emphasized how a gradient gradients would be updated. What are the different gradient descent algorithms, like based on the number of samples. Like one thing, when the model will be updated, that means like how many times, like suppose, and if you take the batch gradient descent, the model is updated after evaluating all the samples, whereas that means all the samples would be considered. So to evaluate all the samples, then we need to move all the samples into the memory, that is to process it. Whereas the stochastic gradient descent, that is for each sample, the model would be updated. So It is like memory efficient because only one sample at a time need to be stored in a memory. So, and these are mainly recommended for the stream like online analysis. And next one is a batch gradient descent, mini batch. Mini batch gradient descent, like the random set of samples as a batch would be selected and evaluated, and then the parameters are updated or the model will be updated. So in this case again, and how the local minimum, when the model, that is the gradient descent, leads to a more that is to get trapped in this local minima, and how the learning rate, like a low very small learning rate, the effect of low small learning rate and also the high learning rate, and these are the concepts we discussed. So then, and how we can select the which is the suitable, right, gradient descent algorithm in this lecture. So thank you for watching this video.